Today's video will cover electron configuration, and for this video it's important to know quantum numbers and what they mean and how to use them. So if you haven't seen my previous video over quantum numbers, now would be a good time to look over that before watching this video. Now, electron configurations tell us the way that the electrons are distributed within the atom. So the first thing you see on here is the periodic table, and I wanted to start off this video with the periodic table. That way I can show you how you can find electron configurations for an atom using your periodic table. Now, usually on the very left side of your periodic table, you will see something like 1, 2, 3, 4, 5, 6, and 7. So you usually have numbers down the left side of your periodic table, and what these numbers are your principal quantum number. So this is n, and n is equal to whatever number resides on the left side, whatever row you're on. And remember, the principal quantum number tells us our distance for the nucleus. So now it's going to be very important to pay attention to the following details, which I'm going to explain. These two rows here represent the S subshell. In addition to these two rows here, helium, which is here, also resides in the S subshell. This box here represents the P subshell. The transition metals in the middle represent the D subshell. And the last two rows down here represent the F subshell. And in the outermost orbital, the valence electrons reside in a certain subshell. Right? So therefore, in these first two rows, the valence electrons, or the outermost electrons, reside in the S subshell. If we're in the P subshell, where the green box is, the outermost electrons, or the valence electrons, reside in the P subshell. And for the D and F subshells, the valence electrons reside in the S subshell. So it's a little bit different than the S and the P's for the D's and the F's. And we'll get into examples of these. So already with this knowledge, we have two pieces of information. We have our principal quantum number, which is here, these numbers down the row. And then we also have our subshell we're in. So now I'll erase all of this so that way I can have some space to write an electron configuration. Now, to write the electron configuration of an atom, I'm going to start with hydrogen. And the first thing you want to do is write the symbol for hydrogen, which is an H. Then you put a colon. And I start off with the principal quantum number. Remember that this is 1, our first principal quantum number. So hydrogen, the valence electron for hydrogen, resides in the first principal quantum number. And remember that these two first rows represents the S subshell. So hydrogen would have 1, and it resides in the S subshell. And the next thing we want to do is denote how many electrons. And to denote how many electrons there are for the S subshell of hydrogen, we would just count how many spaces from the left of the periodic table hydrogen resides. So that's only one space from the left of the periodic table. So we put 1. And the 1 is in an exponential form. So the electron configuration for hydrogen would be 1s1. Now for the next atom, I'm going to use helium. And helium has a symbol of He. And we know that helium resides in the first principal quantum number. So we're going to put a 1. We also know that helium, which is here, resides in the S subshell. So the valence electron for helium resides in the S subshell. Remember previously when I drew those colored boxes, helium was actually, we said that helium is like an S subshell. So that was the only thing that was kind of out of the pattern of the boxes that I drew, was that helium was supposed to be in the S subshell. So we know helium has one S, and now instead of one electron, so I'm going to erase these circles so it can be a little clearer. What you want to do to decide how many electrons are in this subshell is you just count from the left side to the right side. So this would be 1 if it was hydrogen, but we are helium, so now this is 2. So it would be 1s2. That is the electron configuration for helium. And remember when we spoke about quantum numbers that the s subshell only has one orbital. And for every one orbital, there can only be a maximum of 2 electrons. So when you're writing electron configurations, if you see an s subshell, this highest number here, that exponential number that denotes the valence electrons for helium, should never be above 2. It should always only be 1 or 2. Now the next electron configuration, so I will erase these circles again, is going to be lithium, which is here. So lithium has a symbol of Li. And now we're going to get, now we've moved down to the principal quantum number 2. But to write a complete electron configuration for lithium, you start off at hydrogen here, and you move all the way to helium, and then you go to lithium. So when you're reading this periodic table and you're trying to write electron configurations, you read this periodic table like a book. So first, a lithium has 1 s, and there's 2. We have principal quantum number 1, and we have 2 electrons in the s subshell. So we have 1s2. Now we move down to the next row. Now we're on principal quantum number 2. We're still in the s subshell, but now we have 1 electron because it's lithium. Lithium has a total of 3 electrons, 2 in the 1s and 1 valence electron that resides in the 2s. Now continue with beryllium. And beryllium has a symbol of Be. So I'll erase these circles here. And to write the full electron configuration, we're going to do the same thing that we did with lithium. So the first part of the electron configuration of beryllium is 1s2. Then we move down to our second principal quantum number, where beryllium resides. And still in the s subshell, but now we have 2 electrons, because this was the first and this is the second. That would be the electron configuration for beryllium. So now I'll erase this again. Now we're going to move on to boron. Boron is here. It has a total of 5 electrons. And we're going to write the full electron configuration. So we start off moving from left to right of our periodic table. First we have 1s2. So that takes care of these 2 electrons. Then we have 2s2. That takes care of these 2 electrons. We are still in the n equals 2, but now remember that this box here represents the p subshell. So now we are in 2p, and we are in the first electron state of the p subshell. So that would be the electron configuration of boron. So now that we have an understanding of how this works, I'm just going to pick a element off the periodic table. So I'm going to pick sulfur. I'm going to write the full electron configuration of sulfur. So it'd be 1s2, 2s2, 2p6, 3s2, 3p4. If we check here, we see that sulfur has 16 electrons. So we have 2, 4, plus 6 here is 10, plus 2 is 12, plus 4 is 16 total electrons. So this is 1, this is 2, this is 3. I started off at the beginning of my periodic table moving from left to right. So I know that this is the 1, and we're in the S, and there's 2 of them. So that's 1s2. Move on down to the second row, moving from left to right. Now I'm in the 2s still, and now there's 2 again. Moving down here, now we're in the P's, but we're still in the n equals 2. So we're here now. So we're in 2p, and there's 1, 2, 3, 4, 5, 6. So that's how I got that 6 in the exponential form. And if you remember from your quantum number, the p subshell has 3 orbitals, each orbital having 2 electrons. There can be a total of 6 electrons. So for the p's, that exponential number cannot be higher than 6. Now I move on down to the n equals 3. I have 3s12, so that's here, 3s2. And then I have 3, I'm still in the 3, now I'm here. But now this is in the p's. So this is 3p, 1, 2, 3, and sulfur is 4. So now I'll erase. Now we know that n equals 1 here, n equals 2 here, n equals 3 in this row, and n equals 4 in this row. For the D subshell, which is this box here, remember that this equals our D subshell. N is equal to 3 here. So N is equal to 3 here. So imagine that this row should be moved up 1. Let's do an electron configuration of manganese. And manganese is here. And it has a symbol of Mn. So manganese would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And now we're getting into the very last subshell for manganese. And this would be 3d, 1, 2, 3, 4, 5. 3d, 5. So that would be the electron configuration for manganese.